Assalamu alaikum warahmatullah. So today is our lecture 16. And today is the all important eigenvector and eigenvalues. Now, to understand what eigenvectors and eigenvalues are, to visualize these things, you need to have a solid visual understanding of three important topics. So to understand this lecture, you need to have solid foundation of linear transformation, secondly determinants, and change of basis, which is somewhat related to the linear transformation done by matrices. So consider a linear transformation done by this matrix. Let's say you have this matrix A equals to 3 0 1 2. So what linear transformation will be done by this matrix? So let's say before the linear transformation you had this basis I cap and j cap, and after the linear transformation the x axis or the I cap would be stretched by 3 times and the j cap would be landing on 1 2, so it would be something like this. So let's say this one. So let's say this is our changed I cap stretched by 3 times, and this is our changed j cap landing on 1 2. Okay. So if you multiply any vector with this matrix, then this that matrix would be that vector would be knocked off its span. And if you had a vector like this, after the transformation the vector would be transformed into this, right? So it's, as you can see, it's deviated from its span, right? Or span means the span of this particular vector is this one. As you know, the span of a single vector is basically the straight line, and as you can see the vector after the transformation has been deviated from its span. So this was its span and it has been transformed into this. Okay. But there are some vectors that would be remaining on its span even after being multiplied by this particular matrix. For example, any vector on the x-axis. Okay. So let's say you have this vector 2 0. So if you multiply AV, what you'll get 3 0 1 2 multiplied 2 0. So you'll get 3 into 2 plus 1 into 0, and 0 into 2 plus 2 into 0. so we'll get 6 0, and it will be basically 3 times the first vector. So as you can see, it hasn't changed the span, right? So it is remaining on its original span, which was 2 0. So this is just a multiplication, and it has not deviated from the span. Okay, so it only gets stretched on the x-axis. So if I go for a generalized idea, so it was this vector I cap and j cap, this was the basis, and after the transformation of A, the vectors on the x-axis actually remains on the same span. It's just get stretched by the multiplication of the matrix, right? And this is the resultant of the j cap, but is not being used when the vector is on the x-axis, right? So this is the generalized vector form of k0, that the vectors that are on the x-axis, right? There can be another example, that is -1. If the vector is -1 1, if this is the vector, then by multiplying with this matrix, the span wouldn't change. It will only get stretched by some factor. Do it on yourself. Okay, so these special vectors which stays on the same, so at this point you can agree with me that there are some vectors that stays on the same span after the linear transformation, like 2 0 and -1 1, and there are some vectors like let's say 1 1 that actually changes the span after the transformation. So the vectors that stays on the same span after linear transformation are called eigenvectors. So what are really eigenvectors? So eigenvectors are vectors that stays on the same span after transformation. So if they stay on the same span, what does happen? So there is either stretching or squeezing, right? So either the vector gets stretched or gets squished. So by the factor that the eigenvectors get squished or stretched is called the eigenvalue. Alright, so eigenvalues are by the factor the eigenvectors get squished or stretched. So it might sound very similar to the determinants, right? So eigenvalues have very very strong relationship with the determinants of a matrix that you would see very shortly. Okay. So can the eigenvalues be negative? Yes, it definitely can be negative. If some eigenvectors have eigenvalues, let's say -12, that means the orientation of the basis gets flipped. So in linear algebra, I think you already have an idea that by negative value, it signifies that it has to do something with the orientation, right? So if the eigenvalue is negative, you can guess that the original basis is the orientation of the original basis gets flipped. Okay. So let's figure out the conceptual ideas of computation. So the thing is, the eigen. So let's say you have a matrix A, and this V is an eigenvector. Okay. So this V is an eigenvector. So as I said, this V actually stays after being multiplied with A. This V remains on the same span. So let's say it remains V, but it gets stretched or squeezed by the multiplication. So let's say it gets stretched or squeezed by a factor of lambda. So this lambda is called the eigenvalue. But there is some inconsistency here. As you can see, the left hand side is here is a matrix multiplied by matrix multiplied by a vector, and the right hand side is basically, so this is eigenvalue, and as I said, this is a factor, so this is basically a scalar multiplied by a vector. So it can be simplified. So it can be simplified into lambda into I have multiplied it with an identity matrix and then V. Right? So this can be written as A minus lambda I to V is to 0. So this is a matrix, right? This is a matrix, and this eigenvector V was a non-zero vector as the first assumption. So we assume that there is some vector V that stays on the same span V, squished or stretched by a factor of this eigenvalue. So we basically assume that this V is something that is not zero. So this is non-zero vector. So as this is a non-zero vector, so this matrix A minus lambda I is such a matrix that squeezes the space of this non-zero vector into a lower dimension, such as, so as this is, so the span of this particular vector is, a straight line. So this particular matrix is such a matrix that squishes the span of a straight line into a lower dimension, which is a point, right? So this matrix would have the determinant of 0, as this is making the area, or so you know about the idea of determinant, right? So the determinant is such a factor that that measures the how much the area is stretched or squished after a transformation, right? So if you make something or make some area, or if you squish some area into lower dimensions, then that specification corresponds to the determinant of 0, right? So we might say that the determinant of a minus lambda I equals to 0. If you still have confusion, what I did here is refer to the properties of determinant, which is lecture 13, and it is better if you can watch the 3 blue 1 brown video of determinants, as I suggested you earlier. Then you will have a very good visual representation of the determinants. Okay, and if you can definitely ask me in the discussion class if you have confusions about determinants. Okay, so let's find out the method of calculation to find lambda and x, right? So how to solve ax equals to lambda x? So rewriting the equation, we had 1 minus lambda I into x equals to 0. From this, as this x is a non-zero vector, so this a minus lambda I has to be such a matrix that squeezes the space of x into a lower dimension, which is a point. So the determinant of a minus lambda I must be 0, right? So what we have to do is we need to find this lambda first, then find the null space, which will be our x, our desired eigenvector. So let's take one example. So we'll learn the method through one example, and let's say we have a very beautiful matrix, a symmetric 1 3 1 1 3, and this matrix, as you can see, is symmetric and is constant along the diagonal, right? So what was our first thing to do? So we have to get this matrix a minus lambda I. So a minus lambda I is basically 3 1 1 3 minus lambda into 1 0 0 1. So it should be 3 1 1 3 minus lambda 0 0 lambda. So it should be 3 minus lambda 1 1 3 minus lambda. So as I said, that the determinant of a minus lambda I should be 0. So if I rewrite this into determinant form, it should be 3 minus lambda 1 1 3 minus lambda equals to 0, and from this we get this. So the determinant of this matrix is AD minus BC, so 3 minus lambda whole square minus 1 equals to 0. So from this we can get lambda square minus 6 lambda plus 8 equals to 0. So if we solve this equation, we'll have two solutions, which is lambda equals to 4 and lambda equals to 2. So for the eigenvector, we need to find the eigen the null space basically. Okay, so our initial equation was 1 minus lambda I into x equals to 0. So for lambda equals to 4, we have so for lambda equals to 4, we'll have a special matrix for this one, that is 3 minus 4 1 1 3 minus 4. I'm basically copying this matrix, just putting the value of lambda here. Okay, putting the value of lambda of 4, we'll have this matrix, and x is, there will be two elements in x, so let's put x as it is, so it goes to 0. So we'll have minus 1 1 1 minus 1, we'll have x equals to 0. So if we solve this, we know that x would be basically 1 1. So you already know how to solve this solution, but you can use elimination or any other method. I think we have learned two methods so far to solve ax equals to b, so you can apply any of them. So I already know, or you can see it from this row, that if you take 1 for this and negative if there is only negative, there is only already negative 1 here, so if you take 1 and you take 1 here, you get the original null space, right? So you take 1 and 1, then you get 0 on the right hand side. That's easy. So this is one eigenvector, right? And for lambda equals to 2, you have this matrix would be 3 minus 2 1 1 3 minus 2, into x equals to 0. So you'll have 1 1 1 1, x equals to 0. So if you, so again the answer is very intuitive, that is x equals to -1 and 1, right? So these are two eigenvectors. If you want to check, our previous initial matrix was 3 1 1 3, so I'm saying that these are eigenvectors 1 1 and -1 1. So what I'm saying is that if you multiply this vector with this matrix, this vector would be on the same span. Let's check if it is in the same span or not. So a x would be 3 1 1 3 into 1 1. So you have 3 plus 1, sorry, 3 into 1 plus 1 into 1, and 1 into 1 plus 3 into 1. So you have 4 into 4. So it is stretched by a factor of 4, which is this eigenvalue, and you'll get the similar result if you check with this matrix. Alright, so if you take another matrix like A equals to 0 1 1 0, so for lambda you'll have to do this calculation, which is minus lambda 1 1 minus lambda equals to 0. So from this you'll get lambda equals to positive 1 and lambda equals to negative 1. So for the eigenvector you'll have to put these values into here in the matrix form, and you'll get minus 1 1 1 minus 1, sorry, minus 1 into x equals to 0. So from this you get x equals to 1 1, and for this is for lambda equals to 1, and for lambda equals to negative 1 you get 1 1 1 1 into x equals to 0. So this is for lambda equals to negative 1. So x would be minus 1 and 1, right? So from this I can summarize the steps. So summarizing the steps, I can say that to get eigenvectors and eigenvalues, what you need to do is you need to compute the determinant of a minus lambda I, right, which is 0. So you need to do the computation. So you need to find the roots of the polynomials of determinant of a minus lambda I equals to 0, and for each eigenvalue, so you'll get eigenvalues from here, from the second step, and for each eigenvalue lambda you need to solve a minus lambda I into x equals to 0 to find eigenvectors. Alright, so you'll get the number of eigenvectors equal to the number of eigenvalues. So there is one important thing that you might have noticed, that for a n by n matrix, the product of the n eigenvalues would be the determinant, right? So from the previous example, our matrix was 3 1 1 3 if I'm not wrong, and the eigenvalues were 4 and 2, and from this so if this is A, then the determinant of A is basically 9 minus 1 8, and I'm saying that for our n by n matrix, the product of n eigenvalues equals the determinant. So the eigenvalues are 4 and 2, so the product of lambda 1 and lambda 2 is basically 4 into 2, which is 8, which are equal. So for our n by n matrix, the product of the n eigenvalues equals the determinant, right? And there is another relation: the sum of the n eigenvalues equals to the sum of the n diagonal entries, which is trace. So in this case, the trace of A is 3 plus 3, which is 6, and the sum of lambda 1 and lambda 2 is 4 plus 2 equals to 6. So as I said at the first part of the video, or the first part of the lecture, that the eigenvalues have very strong relationship with the determinants. So as you have already seen here, that it does have a relationship with the determinants of the matrix. Okay. So now notice carefully the last two examples. So if I so if I add something with a particular matrix, let's say you have a x equals to lambda x, and you add something with the matrix. So let's say so what was the previous two matrices? It was 3 1 1 3. So for this, the eigenvalues were 4 and 2, and another matrix was 0 1 0 1 1 and 0. So the eigenvalues were 1 and -1, right? So what really happened here is that with this matrix I added, so if this is A1 and this is A2, so with A2 I added 3i, right? I added 3i. So as you can see, the diagonal entries have been changed, right? And what is the change in the eigenvalues? The eigenvalues also changed by a factor of 3. So do you find the coincidence here? Not a coincidence, but the mathematical logic that is being worked here. So this one, this one, this one, this one, so all these are correlated, right? So the thing that is happening right here is that A plus 3i is also, so yeah, so this can be simplified as ax plus 3ix. So ax is lambda x, so this is lambda x plus 3ix. So it can be written as lambda plus 3i to x. So the eigenvalues are also being increased proportionally, right? So if ki is added to any matrix, the eigenvalue is increased by k, right? And the eigenvector, as you can see, remains the same. The eigenvector remains the same. And there is a common misconception that if ax equals to lambda x, where so this is the eigenvalue, and bx is equals to alpha x, so this is the eigenvalue as well. So if you add this to a plus b into x, then lambda plus alpha into x, so this is wrong, right? This is only right if the eigenvectors are same for both the cases, but it might not be the case. In most of the cases it is not true. So this is not true because the eigenvector that is x might not be same for a and b. Okay. Now we are in the last part of the lecture. So let's take a rotation matrix. So if you take a rotation matrix, that does the 90-degree rotation, so it'll have 0, -1 and 1, 0. So in this case the trace which is lambda 1 plus lambda 2 is 0, and the determinant of this matrix is lambda 1 into lambda 2 is 0, -1, so it should be 1. So by applying the formula of the factors, the equation would be lambda square plus 1 equals to 0. So from this we know that lambda equals to, so did you get from where I wrote this? So if you have two factors of two solutions of second degree equation, the second order equation, sorry, alpha and beta, then you can write the formula as x square minus alpha plus beta into x minus plus alpha beta, so equals to 0. I hope this thing is correct. Yeah, so from that we get here, and if we solve this equation, we know that it would be plus minus root over minus 1. It should be positive I and negative I. These are the two solutions. It is very intuitive. After you rotate a vector with the rotation matrix, it is the vector cannot be on its own span anymore, only if you're not in an imaginary space, right? So after the rotation matrix, any vector, actually no vector can be on its own span, right? So only if you're in some imaginary space, then you can reverse the rotation and get back the first vector, or the initial vector. So from this lecture so far, I think you have an idea. So we have worked with several symmetric matrices. So you saw that for the symmetric matrices, you have very beautiful eigenvalues and eigenvectors, right? So the more symmetric the matrix be, the better your eigenvalues would be. Okay. So not every vector or not every matrix would have multiple eigenvectors. For example, if you take a triangular matrix like this, A equals to 3, 0, 1, 3, then this lambda 1 plus lambda 2 would be the trace, which is 6, and the lambda 1 into lambda 2 would be the determinant, which is 9 minus 1, 8. So applying this factor method, we have this equation, lambda square minus 6 lambda plus 9. Oh, did I make any mistake? Oh, the determinant is 9. Sorry, it should be 9.